All right, day 9. As I am starting to read this, this is one of those days where they kind of just say a bunch of stuff. I'm pretty sure that plank flanks aren't going to be relevant to us really at all. So the rope has to be short, head and tail must always be touching, diagonally adjacent and even overlapping both count as touching. So we've basically got a rope, and the rope is a head and a tail. And if we scroll down, it gives us kind of some of the rules. So if we have head tail, this is touching, head tail is touching, head tail are in the same spot and they're touching. If the head moves in the same direction that the head and the tail are, then the tail just closes the gap by 1. Otherwise, if the head and the tail aren't touching and aren't in the same row or column, the tail moves 1 step diagonally to keep up. So if this head moves up, this tail has to move diagonally into this spot below the head. Same situation here. If the head moves in a direction and the tail is not connected and not in the same row, then it has to move 1 diagonally into behind the head. And I think actually the shortcut here is that this always turns into right behind the direction the head moved. So we don't actually even need to calculate this. We just know, because if the tail is not touching and it's not in a row or a column with the head, then whatever direction the head just moved is where that tail is going to end up, because that's where the gap was created. So we have some input. We've got R4, U4, L3, D1. These are directions. The key insight here is that we don't move in jumps, we move in singular steps. So we move R for 4 steps, U for 4 steps, L for 3 steps, and so on. And this kind of long output shows that. So the answer is going to be how many positions the tail visited at least once. So every position the tail has ever been in, basically. S marks the starting position, which the tail also visited, and hash marks all of the positions the tail has visited in the very long input that is right up here. If you count all of those, you get the number 13. So simulate the motions. How many positions does the tail of the rope visit at least once? So let me set up our test. Same test format as we've had every other day. We're ignoring part 2 until later, but part 1 is right here. We do need this input, this test input. So we drop that into the tests with the input string. We are going to need a parser, so we can do separated list 1, new lines, separated pair, and then I think this will be alpha 1, tag space, complete U32. I think I have an extra paren here. Of course, that gives us back a string slice and a U32. So we'll end up with a vec of string slices and U32s. Now we could change this as well. So let's cover the parser first for a second. Our input is this, right? So we've got R space 4, new line, U space 4, and so on. So we do a separated list of new lines. That gives us every line individually. We do a separated pair for each line with an alpha on the left-hand side, a space in the middle, and a U32 on the right-hand side. And that just gives us the vec of the name or the direction on the left and the number on the right. Now we have a couple options here. We could write an enum direction that is left, right, up, down. So we can pretty quickly write a parser here using all of the knowledge we've taken from the previous days. We write a direction parser that takes the input. We take an alternate parser that will parse either a character of L, R, U, or D. We map over those parsers and we change them out for the relevant enum. So if we successfully parse an L, then we'll get a direction left and so on. That makes dir up here a direction, which we can just return. So now instead of alpha 1, we can do a direction here, and we're left with a vec of directions and U32s. So because I want to be able to move singular steps at a time and not have to worry about any of the repetitions or anything, we can take the vecs that we parsed out of the separated list, iterate over them, and then we can flat map. Flat map allows us to build up a structure that can be iterated over that will be flattened into the result output. So if we return a vec here, for example, what we'll end up with is a single vec of all of the items instead of a vec of nested vecs. That's what the flat does. It's the same thing as doing map and then flatten. So if we map over this, we get the direction and the number of times it needs to repeat. The vec macro really helps us out here because we can take the repeat value, which is a reference to a U32 in this case. So we need to dereference that to get the U32 value and then treat it as a usize because that's the type that Rust uses for all indexing operations and things like that. Now the syntax here is supposed to be the thing you want to repeat, semicolon, the number of times to repeat it. But we have a problem here And I stopped on this very specifically so we could take a look at the error. It says the trait clone is not implemented for direction. So if we want to return a capital D direction here, then the enum has to include clone on it if we want to do it like this, basically. The fix is super easy. We can derive clone here. And then it warns us that we also don't implement the copy trait. So we can copy this here too. And now when we dereference the reference to the direction here, we end up with a copy of that set into this vec. So if we rename the parser moves and we apply it, then we debug move set, which we can't do yet because we haven't derived to debug on our enum. So we've got copy and clone, and now we'll use debug. And right now I'm running check, so I'm going to run test now. And then we get this list. So we've got right 3 times, up 4 times, left 3 times, down once. So if we look at our map, right 4 times, up 4 times, left 3 times, down once, right 4 times. I need to get my contacts fixed is what I need to do. Down once, left 5 times, and then right twice. So we get a full list of everything that we actually need to process. So I don't think it gives us any starting position, any special starting position anyway. It looks like we always start in what is effectively 0, 0, or rather 0 length of the number of vecs. It doesn't say we have a grid anywhere of any specific size. So I'm going to assume that this is 0, 0, and that everything we move to is going to be, in this case, it happens to fit inside of this grid, which is why it's being shown like that. But there is no like guaranteed it's going to stay inside of this grid kind of thing. So the way that I'm going to set the problem up then, because we don't actually know what the grid is like, is we'll start with the head at 0, 0, we'll start with the tail at 0, 0, and we'll start with a hash set of the tail positions. I do a hash set of the tail positions here because then I don't have to worry about inserting duplicates of the position that we're in. So if we look at this, we can say hash set from an array of tail, and that'll give us 0, 0 as one of the keys in the tail positions. This does have to be wrapped in some kind of iterator or array or something like that. So I'm just going to keep it inside of this square bracket. And then we're down to actually implementing the moves. So we're going to match on the head move. I'm going to use Rust Analyzer here. So on my Mac, that's Command dot to bring up this menu, fill match arms, which writes this out for me. And then we've got direction left, right, up, and down, which we can handle. If we look at the types of these, they're already I32s. So I32s can go positive and negative. And I assume that we don't need anything bigger than a 32-bit integer. So that's what we'll stick with. If we go left, we need head to be mutable, and we need tail to also be mutable, and we need tail positions to also be mutable. So I'm using the left position of this tuple as X and the right position as Y. So we can do head.0 minus equals 1 to move it left in that direction. We can do plus equals 1 for the right, and plus and minus equals 1 for up and down. So this moves the head into whatever position it's going to be in, and we now need to calculate whether the tail is in range of the head. So we have a couple options here. I think what I'm going to do is create X range and Y range. So X range is going to be head.0 minus 1 dot dot head.0 plus 1. And the Y range is going to be the same thing. So if we log that out, we are seeing a bunch of the output. I didn't log out the actual head position, but we can guess it from these. So if we are at 1, 0, then we get a range from 0 to 2 and negative 1 to 1. Now, you could just iterate over these, and that would be fine. But I'm going to use this opportunity to add itertools into our tool belt. So I'm going to use cargo add itertools. Cargo add is available as of Rust 1.64, I think. It's fairly recent in terms of releases, but it has been around for a number of weeks now. Itertools specifically offers a trait called itertools. This is called an extension trait. It extends the number of functions or it adds functions to basically the iterator trait so that we can call them. It does this by basically saying we're going to have the itertools trait. Anything that implements iterator also implements itertools, and we implement all of those functions on the itertools trait. So then we automatically get those for anything that implements iterator. Now, why is this nice? This is nice because we can do X range dot Cartesian product Y range. Now this will look real weird if you've never seen this before. So let's do this. Let me show you what this outputs. We're going to collect into a vec of I32, I32, and I'm going to get rid of X range, Y range. And we're going to run our tests again and take a look. And what I'm realizing as I'm scrolling up through these is I messed up the ranges. So the ranges need to be inclusive. So we want the head -1, but we also want the head +1. So if we make them inclusive, then we get the full lists here. And the full lists are really interesting. So Cartesian product, if we go to the itertools docs and we look at Cartesian product runs an iterator adapter that iterates over the Cartesian product of the element sets of two iterators, which if you don't know what Cartesian product means, doesn't mean a lot. But if we look at the implementation here from 0.2 Cartesian product, and I think these are the characters alpha and beta, right? It doesn't really matter, but note that the output of the Cartesian product for ab.cars, which is an iterator, and 0.2, which is a range, which can be turned into an iterator, gives us 0 alpha, 0 beta, 1 alpha, 1 beta. It gives us all of the combinations of one element from the first iterator and one element from the second iterator. This is really nice if you need to construct a range of grid points, because you can take the bottom and the top range for both directions. And once you get those ranges, you can do a Cartesian product on them and you get a list, an iterator of all of the grid points that you need to care about. So we're going to do that Cartesian product and we're going to call any on it. And I'm just going to call this tuple, or actually let's call this tuple. And then it's going to be tuple equals tail. So what we've done here is we've taken the tuple for X and a Y position for the entire grid, including this position that the head is on. And we've compared it to the last position of the tail, which will tell us if the tail is still connected to the head. If the tail is connected, we're done. If the tail isn't connected, we need to move the tail. And the insight that I had when we were doing the problem in the beginning, when we were reading it, is that whatever direction the head just moved is the direction we need to fill in the opposite direction for the tail. So if we match the head move again, we can tell which direction the head just moved in, and we already know where the head is. So we can set new tail equal to head.clone. And if the head just moved left, then we need to move one to the right, and that's where the tail is. So we're basically reversing the calculation we did earlier. And that's all for new tail, which I forgot to make mutable. And when we're done, we can do tail equals new tail. And the other thing that we need to do here is, what did I call our hash set? Tail positions. We're going to tail position. We're going to insert new tail. And then tail positions dot length dot toString, because we need this toString, should be the right result. And our part 1 test passes. So hopefully our part 1 will pass. Now I haven't actually gotten my puzzle input yet, so I'm going to go do that now. And then we need to run part 1, and hopefully 5,874 is the answer. And it is 1 gold star. So we did the movement correctly. So recap, we have this input, R4, U4, L3. What this is a number of steps that we need to take for each of these directions. So this starts out as move R 4 times in the right direction, move up 4 times, move left 3 times, and so on. We write our parser, moves, to be a separated list of new lines, which gives us lines. What we're left with is each of the lines are a separated pair of a direction, space, a number. The direction is a character parser, which we map over, if it's successful, to turn into the right enum. That makes this a direction, and we return that direction from our parser. So what we end up with in vex is a vec of directions and the number of times we need to move in that direction. I like simplicity, so what I did is I iterated over that vec and I flat mapped it. Flat map means that when we create a vec here, that this vec will get flattened and we'll get a single vec out of all of the vecs. So in this case, it's like running map, transforming it, and then running flatten. In this case, we take the direction and the number of times we need to repeat it, and we use the vec macro syntax, which is wonderful, to set the value of the direction a number of times, which has to be a usize. We collect that into the vec and we send it back through the parser. So we end up with a move set that is individual steps. So we'll get right, 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 left, 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 that kind of thing. We initialize our head state and our tail state to be 0, 0 because we have no idea how big this grid is and it doesn't give us a starting point. So we choose a starting point that is fun for us, I guess. The tail positions is a hash set because this will keep everything unique, and then we don't need to worry about whether something is already in this hash set or not. And we initialize it from a single element array that is just the current tail position because the tail starts in the tail position. We iterate over the move set, which is a direction, to put the head in the right spot. This always happens. The head always moves, either one left, one right, one up, or one down. Then we need to look in all of the spaces that the head is on, as well as all of the surrounding spaces around it. This gives us about 9 grid points that we need to check. We can set up the grid points that we need to check by doing head x value -1 and head x value +1, same for the y direction, which gives us the range of x values and y values that surround the head. We can use that x range with the itertools extension trait to run Cartesian product with the y range. This gives us a list of every value in x matched with every value in y. What this effectively gives us is a 3x3 grid of all of the positions that we need to check. Because this is still an iterator, we can run any on it and take the tuple that we get from this Cartesian product and test it against the current position of the tail. This will tell us if the tail is connected. If the tail is connected, then we don't need to do anything. If it's not connected, then we clone the current head position and we can match again on the direction the head just moved, and we reverse the calculation. So if the head went left, then the tail has to be one spot to the right of it. Once we calculate the new tail position, we set that to tail and we insert it into the hash set. At the end of this, then the hash set is all of the positions that we visited with the tail. So we can just get the length and we toString it. So now what we've got is a rope of 10 knots. Using the same series of motions as the above example, but with the knots marked H1, 2, etc., the motions now occur as follows. So we do get to set this up ahead of time, and we're probably going to want to change our method of calculation to be an array or a vec of something. And then we do basically the same calculation all the way down the rope. This is a very large amount of input to check. Now you need to keep track of the positions of the new tail, 9 visits. In this example, the tail never moves, okay. So it only visits one position. However, be careful, more types of motion are possible than before, so you might want to visually compare your simulated rope to the one above. More types of motion are possible than before. Why would more types of motion be possible than before? Here's a larger example, H1, 2, 3, 4. Oh, it's skipping all of the, that's not fun. All right, so we kind of should probably print this out at some point and check it. We have to simulate a 10 element rope. So what I'm going to do, I think, is start by copy and pasting our part 1 example in, and then do we not get 36 is the new input, but that's for the larger example. What is for the smaller example? So it's 1 for the smaller example, and then we'll pull in this as well, which is 36. So this is going to be 1, and then assert equal process part 2 is going to be this input, which I'm going to make sure to take the space out of, comma 30, that's 26, 36. Make sure the parens get right. Okay, so this test should pass when we're done. And we have to run this calculation for every element pair. So we have to move the head, then check the tail, which will move, after which point we have to check the next tail and move it, and check the next tail and move it. So for each move, we have to run this head move. And then we have to iterate over everything. Is that right? So first of all, this needs to change. So let's write this so that it's an array. So let rope equals 0, 0, 0, 0. And actually, let's write this like this. I think that will work. Let's debug rope and comment this stuff out for a second. We'll cargo watch test, and we will enable the ignored test. And I'll comment this one out too, because I think that is the problem. Tail positions doesn't exist, so we'll comment that out too. We'll comment everything out. Why not? And then I'm just going to return to do here. Look at my wonderful error message. Okay, so rope is 2 elements that are 0, 0. So we should be able to just change this to be the number 10 later, which should fix it. So let's get back into writing everything. Tail positions is going to be from rope.last. So that'll put us at 0, 0. And then for head move and move set, match the head move. And then we need to do not head here, but rope 0. And then here's where we need to loop. So we do need to unwrap rope.last up here because we want tail positions to be a hash set of actual values here. Although the references are fine too, actually. Let's make it the value though. So now if we look at the type, it should be a hash set of I32, I32 tuples. I feel like I want to iter mute here. Can we do tuple windows on the mutable reference? I don't actually know. It looks like no. It looks like we have to clone for tuple windows. If this is iterable, then we get to keep all of our logic exactly the same, which would be really nice. So tuple windows requires the item to be clone. Mutable references are not clone, so that's unfortunate for us because it's not going to be as easy as I wanted it to be. What did we use the other day? Array windows. So the windows method exists on slices. We can have a slice here. We do need to make rope mutable up here if we're going to mutate it. So we can try to fight with the borrow checker to do something like this. We can try to windows with mutable references, but no matter how we write this, it isn't really going to work. But there is a crate called lending iterator. And if we scroll down, we say mainly it allows lending mutable reference items, which means it can handle the infamously challenging Windows mute pattern. So if I cargo add lending iterator, and we use lending iterator prelude, and we run Windows mute, and we do something more like this, because you'll notice that Windows mute returned from Windows mute is not an iterator. This is because I believe the lending iterator uses streams under the hood, and streams, the stream trait specifically, requires that we use while let. So we can do the rope windows as a mutable, what we'll call an iterator, but is actually a stream, with the new Windows mute function that takes a generic const of 2, and we can do while let sum, and we use the special keyword ref to get a reference from this destructuring, mutable head and mutable tail, which allows us to mostly keep all of the logic that we just had. The only difference being that we don't do tail positions.insert here, because the only time we can do tail positions.insert is after we've modified everything. So then we get rope last unwrap, and we need to dereference that. So I'm not getting the result that I was expecting. Oh, right, because my rope is still 2. So how long is the rope? 10? So H through 9 is 0 through 9 is 10. Do we have 10 of them here? Let me debug rope quickly. I'm going to go with yes because we confirmed this earlier. But 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so we do have 10 rope items. We are getting 1, 2, 3, 4, 5, 6, 7, 8, 9 results out of this. If we bring it back to 2, we get 13, which is the correct answer for part 1. So we're left with, we've implemented this correctly, and there are moves or positions that the rope gets into that we are not calculating or not properly managing. So it's going to be really rough to print all of these out without printing, without pretty printing them. So we can at least print out all of the positions, and we'll change this back to 10, which is going to be rough to read. I'm going to bring over our initial state here. So this is, make sure this is part 2 here. We have 10 knots. It says using the same rules as before, using the same series as motions. So we start off with everything at 0. Then the head moves to 1, 2, 3. So we should have 4, 3, 2, 1, which is what we do have here for the first 4. 4, 3, 2, 1, 0. These don't move. And then what? H goes up 1 to 4, 1. Everything else stays. And then we immediately break, I think, right here. So we end up with 4, 2, 4, 1, 4, 0. That doesn't look right. And then 4, -1, 4, -2, 4, -3. That doesn't look right. I think we're tuple windowsing the wrong way. So let's see. Print line, debug format, head tail should give us what? A lot of output. So everything is zeros. I almost feel like I want to enumerate this, but so we get 1 0 0 0, 2 0 0 0, which becomes 1 0 0 0. We get 3 0 1 0. This is the, that doesn't look right to me. 3 0 1 0? No, 2 goes to 3. Yeah, 3 0 1 0, which becomes 2 0. 2 0 0 0. 0 0 becomes 1 0. Okay, so far so good. And then we get to 4 1 3 0, right? Because we went up 1, and that looks okay. And then we get 4 2 3 0, which becomes 4 1 2 0. That doesn't look right. 4 1 4 1 doesn't look right. So we move from 4 1, which is 1 up,
and all on the ground. So it's this position here, 4 1 to 4 2 4 1 4 2 4 1 3 1 2 1 1 1 4 2 4 1, and then this is supposed to be 3, right? Ah, that's because we are not propagating the move. Okay, that'll be interesting. So the head move is going to be something that we need to keep track of. So let last head move equal head move dot clone, right, for the first call, which gives us a direction. And then tail is connected. These will be the head moves. So last head move for all of these. So they're all right now. So if we go left for the head move, right, then the tail moves to the right. Tail moves to the left. Tail moves down. Is negative down? I think negative is down. Tail moves up. I didn't set that as mutable, did I? I did not. Mute last head move. And then these all need to change the value, not the variable binding, which direction cannot be dereferenced. So what's the issue here? Oh, because last head move is inside of this iteration, right? No, it's not. Of course, I'm absolutely dumping output here. So let's get rid of the print line. Do we have another print line happening? We do on the rope. That's after. So I think that's okay. So rope, yada, yada. We have a warning on last head move. Why do we have a warning on last head move? Value assigned to last head move is never read. That's because we're not assigning it to this. So let's do a print line, last head move, text document formatting failed. Okay. So the last head move, if it doesn't need to move, doesn't matter because the tails will be connected. So we need to be logging this out in here for when it matters. So if we get all the way up, we get a right, then we get a left. That doesn't seem right. So we need to determine how the last one moved, or at least tell the next one where to move to. Ooh, interesting. So this head move needs to be, wait, did I do this wrong actually? Now that I'm thinking about it. We have head move, we have the tail move, but we don't have the diagonal move. Does it never move in diagonal in the first, or did we just get lucky? Okay, the shortcut we took in the first is kind of biting us now because we can no longer set it exactly equal to the position based off the last move because we still need to calculate which direction it moved in. What is the... So I think we actually need to program this move, this diagonal move right here. So does this always equal, doesn't equal exactly one match. So we could do two Cartesian products and do the intersection of those two. We would find two spots if it was diagonal, and then we would choose the spot that was on one of the same rows as H. So really what we would want is the range that fills a T here, because it'll never go into one of the corners for H, and then the full range for T, the tail, and whichever the matching position is, that's where it goes. So if we're not connected, then we need to do this diagonal movement. If we are connected, then we're good, right? No, if we're not connected here, yeah, okay. So if we're not connected and we're in the same row or column, we need to move in that direction. If we're not connected and we're not in the same row or column, we need to do the algorithm that we just talked about to find the diagonal movement. Dang, I thought I was so smart with that part one too. Okay, so I don't think we actually want the last head move at all. I think what we want is the tail is not connected. If, let's comment out new tail for a second. If head.0 equals tail.0, do something. Else if head.1 equals tail.1, do something. Else diagonal, right? So if the x's match and they're not connected, we need to move the tail towards the head in the y direction. So if head.1 is greater than tail.1, we get new tail here. New tail. Actually, we can just mutate tail now, but so we don't need mute tail. We can do new tail.1 plus equals 1. Right, we got rid of new tail. So tail.1 plus equals 1. So if the head and the tail are on the same x plane, that means they're vertically aligned. So we need to move tail towards head in the positive y direction. Otherwise, we need to move it in the negative y direction. And then we do the same thing here, but instead of dot 1, we do dot 0 to move the X direction. And otherwise, we do let head range. Do we have head range already? Yes. Yes, we do. But head range isn't what we want there. We want specifically the 4 sections. So we can set that up ourselves without ranges or without ranges. So let head range equals head.0, head.1, presumably in some capacity 4 times. So we do X to the left, X to the right, Y down, Y up. So head cross positions. And then we need all of the tails. So we need to do the same thing we did for Cartesian product, but these are going to be for the tail positions, not for the head positions. So this is all going to be tail. Then we need a Cartesian product. We need to find tuple, which is going to be the tail range equals, or not equals rather, but this is going to be the tail tuple. And we're going to do head cross positions dot contains tuple, which is going to be an option. But if we're here, we're always going to have to find one. So new tail is going to be that. And then I think we've already mutated tail in the other positions. So we can mutate tail here. And then at the very end is when we do our little thing. Of course, we're unwrapping on a none value on 171. So that's where I just put this unwrap. Not being able to find a tail that matches with the head cross, a potential tail position anyway, that matches with the head cross positions. That doesn't feel right. So we've got head x minus 1y, head x plus 1y, head y minus 1x, head plus 1x. Cartesian product on the 2 ranges for the tail between -1 and +1, -1 and +1, which gives us the 3 by 3. And then we need to find this tuple. Am I doing the comparison wrong? So this is an I32. So right. We end up with 4, 3, 2, 1. 4, 1, 3s, 2, 1 on 0. And then this is the next move. So 4, 2, 4, 1, 3, 1, 2, 1, 1, 1. I think that's accurate. Ugh, this page is so long. Initial state, that, and then 4, 1 with those. Then 4, 2, 4, 1, yes. 3, 1, 2, 1, 1, 1, yes. 3, 1, 2, 1, 1, 1, and then 0, 0. And then this is 4, 3, 4, 2, 4, 3, 4, 2. 3, 1, 2, 1, 1, 1, 4, 3, 1, 2, 1, 1, 1. So that's accurate. And then there's something wrong. What's wrong? So let's do a debug output of the Cartesian product, I guess. This is for debugging purposes. So I'm just going to clone the ranges to see if we can get them output. And then I'm going to debug head cross positions. And I'm going to scroll all over the place and see if we can find the one that we care about. So 4, 3, 4, 2, 3, 1, 2, 1, 1, 1. 4, 3, 4, 2. Nope. 4, 3, 4, 2, 3, 1, 2, 1, 1, 1. So this is the one that we care about, right? This is the one that we're breaking on. And the head cross positions are 3, 3, 5, 3, 4, 2, 4, 4. 3, 2, 3, 5, 3, 4, 2, 4, 4. That's the head for the H. That shouldn't be getting there, right? Head cross positions. We don't need last head move anymore. We have head here, right? If the tail isn't connected, we have 2 up moves. And then we hit, why do we hit that? I guess it's for this 1, right? So we go up, up, and then we're calculating this position, which is correct, to match the 2, which should match on 1, 2, 3, 4, 2. They should match on 4, 2. 4, 2 is right here inside of the head cross positions. And the Cartesian product includes 4, 2 right here. So we get an up. So which number panics? This number panics, whatever this is. This is 1, 2, 3, 2. So 0, 1, 2, 3, 2. So it's this 4. Is it this 4 because it's pulling the 5 diagonally up? So 4 and 5 are diagonal there. But 4 moves up, and therefore so does 5? That's a new movement that I think we can solve for, but it's a new movement. Basically, if 5 is here when we do this move, then the top right corner and the bottom left corner meet and they have to match. So let's get rid of that. And then the cross positions, we're going to do the same thing for head again. Basically, in the first case here, we match on 2 potential positions. So I guess if we match on two potential positions, we could also just prefer the one that's parallel. So instead of head cross positions, let's comment that out and let's do head cross positions. And this isn't going to be any. We can do a dot collect here, vec. So if we do that vec, then this is a vec of I32 tuples. The head cross positions are now all of them. So the maybe new tail Cartesian product find needs to be, do we have a find all? I guess find all is filter, right? So tuple head cross positions contains tuple, which will always be a vec, right? No, it's always going to be an iterator. So we collect this and we need to specify the type, which is going to be a vec of I32s, or it's not going to be a vec of I32. It's going to be a vec of tuple of I32s. Sorry, I got that wrong. Vec of tuple of I32s, maybe new tail. If maybe new tail dot length equals 2, do something else. Let's do this. Let's do match here. Match maybe new tail dot length. We're going to do 1 for 2. We're going to do 1 for 1. These are the two cases we're expecting. And then we're going to do 1 for anything else, which is going to panic. I'm going to say unknown tail length for the panic. And for 1 is really easy because we do maybe new tail 0 is the new position. So we do tail equals this. And then we have a problem with the tuple up here. Why do we have a problem with the tuple? Because it's a reference. Why do we have a tuple problem? Oh, value borrowed after move. Where are we using it first? Oh, when we debug it? Okay. Well, that's easy. Just get rid of the debug. The other thing we can do is add a reference to that debug. Or we could have cloned it or whatever. We already hit an unknown tail length. So there is a situation in which there is no matching, or there's many matching maybe, I equals 0. How could there... I'm going to assume that because we haven't written the second one yet, that's why. That's why we're failing. So we can do this again for the head positions. This is getting very verbose, but I'm doing this because I want to make sure that we get this right more than I'm trying to be concise. So we'll call this new head cross positions, and we say maybe new tail dot iter dot find. We do the tuple here. New head cross positions dot contains tuple. We next equals that, and then tail equals next. And hopefully the 0 problem goes away. This is an option. This always has to find one now, and that is still a reference. So we need to dereference it, and it looks like our test passed. So that's everything. Both of our tests are passing now. That was a journey. The shortcut that we took for part 1 didn't work for part 2, and we had to debug it, which involved a little bit more code. That's totally fine though. I think we could take this down a little bit, or at least rename some of these variables. I think that we're good. So we're going to run the bin for part 2 and forget that I included some debug somewhere. Let's get rid of rope, and then let's get rid of rope down there, and we'll run it again. 2,467 is our answer, and it's the right answer. Perfect. So we can return to our advent calendar and see how much time I spent debugging. I did start late today, so it's not as much as it looks like. But we can see our nice ASCII art now, which is wonderful. So people have said they want to see the debugging, so I'll leave everything in today. That'll make it a little bit of a longer video, but let's go over process part 2. So for process part 2, we changed our representation of the rope to be from 2 different head and tail elements to being an array of 10 elements. This syntax means that we build a rope with every knot at 0, 0 for 10 knots. We then set the tail positions hash set to have a rope with the tail position in it. We then iterate over the head moves. The head will move in a direction. This is exactly the same as part 1. It moves either left, right, up, or down. So we mutate that. We pulled in a new crate, which is really exciting because we needed to add Windows Mute. Windows Mute, of course, only comes in from the lending iterator up here at the top crate. So that's super exciting. I think this const generic can be inferred, but I'm going to also leave it there. So you can see that it is actually inferred. If we run part 2, it still runs and gives us the answer. I feel more comfortable with it being there so that I don't ever modify this array. But it is entirely inferable. And it's inferable from the size of this array specifically. I just know that we always want 2 here, so I'm going to put the number 2 there. And then because Windows Mute from the lending iterator crate is a stream and not an iterator, we need to use while let. At least I believe it's a stream. I would like to go to the repository here, please. Lending iterators, very interestingly, are a thing that are enabled by GATs, I believe. So if we go into source here, see there's already a mention of GATs here. HKT is short for higher kinded type. This is the Windows Mute file. Windows Mute returns a Windows Mute struct. That struct implements lending iterator and has a macro, attribute macro for GAT on it. So I think this is going to look a little bit more complicated than I want to go over today. So yeah, this is way more complicated than I can go over at the end of a video. Suffice it to say that this uses pretty advanced code to implement GATs with some macros and some fanciness. So the reason that we can't do rope windows as an iterator is I believe there is no iterator implementation here, but what it does is it implements the next function so it looks like an iterator. Because it's not actually an iterator, we can't for loop over this and we have to use while let because we're matching on the return value of the .next function, not relying on the fact that this implements iterator. So while let .next returns an option. Sum is going to destructure. We're going to use ref to get a reference to, and specifically a mutable reference to, these 2 variables that we're destructuring out, which allows us to use the exact same code, pretty much, that we had in part 1. The big difference is if the tail isn't connected, we've changed to use one of a couple options. So if the tail isn't connected and it's matching either on the X plane or on the Y plane, then we move it along that towards the head. Otherwise, we do this kind of finagly thing where we build up the ranges for the head. This is no longer cross positions. This is actually the 3x3, which I can rename right now. I'm going to name it head 3x3. So the 3x3 grid around the head can take the range for the X and the range for the Y and use Cartesian product from the itertools trait. We can do the same thing for the tail. So we have 2 3x3s. We can filter on the tails 3x3 to check to see if the heads contains any of them. We filter all of those out. So maybe new tail will have a length of 2, 1, or 0. In this case, we only ever have 2 and 1 in a properly functioning application. So we match on length for 2. If there are 2 items, we need to make a decision. If there's 1 item, we can just set the tail, because we have the mutable reference, to the maybe new tail value at 0, at the 0 index. If we have 2 items, we want to prefer the position that is in line with a head rather than being in one of the corners. Why? I don't know. That's just the way it works. I think we could have easily preferred a different move or something like that, but this is the way the puzzle wanted us to do it, so that's the way we're doing it. So instead of getting the 3x3, we now have a cross for the top, bottom, left, and right positions around the head. We iterate over maybe new tail, and we find the cross position that contains one of the tuples. And when we find that, because we have to find that at this point, because of the way the puzzle is set up, we set that to the tail. And then outside of all of that, after we've iterated through all 10 knots, we add the tail to the tail positions hash set. Now, this Windows Mute is the key to this working. So we modify the head with head move, and then we iterate over overlapping windows. So items 0 and 1, 1 and 2, 2 and 3, and so on. So this head is always the first element, the leader element, and this is always the tail element or the follower element, even if they're not necessarily the head of the rope and the tail of the rope. All right, so part 2 got a little bit more complicated. I hope you enjoyed it. If you have any questions, as always, leave them in the comments, and I'll talk to you tomorrow. Have a great day.